Hi, I'm Professor Len Kelly, and in this presentation I want to discuss testing procedures associated with multiple linear regression models. You'll notice in Chapter 7 that we explore the decomposition of the sums of squares as a means to test the significance of individual or sets of predictor variables in the presence of other regressor variables. This is the focus of this presentation. Of course, you will also want to review carefully the material regarding standardized regression models and multicollinearity, which are also discussed in Chapter 7, as these are important and certainly useful topics too. We have already seen the multiple linear regression model containing p parameters or p minus 1 regressor variables, and we've discussed our normal regression model in light of the random error term epsilon being normally distributed with a mean of 0 and a constant variance sigma squared. And we've also generated the matrix notation associated with the multiple linear regression model, and used matrix algebra to come up with some of the key results, one of which is the finding of the estimated regression coefficients associated with a model. The ordinary least squares estimators can be obtained by taking x transpose x inverse times x transpose times y, and what we see, of course, then is that these estimators are linear combinations of the observations, and because we have assumed that the random error terms are normally distributed, these estimators are also normally distributed. And in fact, we have demonstrated, you've proven actually, that these estimators are unbiased. That is, their expected value is equal to the value of the parameter that they're being used to estimate. And we've also generated the, using matrix algebra, we've also generated the variance covariance matrix associated with these regression model estimators. Of course, the value sigma squared is generally unknown to us, but if we did know it, then we could compute the variance associated with our estimators, and taking their square root, then the standard deviation, and so we could subtract off the mean, divide by the standard deviation, and because the b sub I are linear combinations of the observations, that is, they are normally distributed, then we know that we've this statistic b sub I minus beta sub I divided by the standard deviation of the beta sub I, the b sub I, would have a normal 0, 1 distribution. The unfortunate thing, of course, is that we generally don't know sigma squared, but we do have a great estimator for sigma squared, and that is the mean squared error. And so we can replace sigma squared with mean squared error and find the estimated variance covariance matrix associated with our regression estimators, and then pulling off the main diagonal of that estimated variance covariance matrix, the standard deviation, the estimated standard deviation associated with each of the estimators, we could produce a test statistic which has a t-distribution, in this case with n minus p degrees of freedom. And we can use this test statistic then to test the significance of a particular predictor variable in the presence of the other predictor variables that are in our model. That is, we could test the hypothesis that beta sub I is equal to 0 versus beta sub I is not equal to 0. And of course, if beta sub I is equal to 0, then the variable associated with that regression parameter coefficient would certainly be insignificant. On the other hand, if we can conclude the alternative, that is that beta sub I is not equal to 0, then that indicates that the variable x sub I significantly increases the explanatory power of the model. Now, it's important for you to recognize that when we're dealing with multiple linear regression models, these tests are being conducted in the presence of the other variables that are in the model. Now, the nice thing about it is Excel provides this output for us if we use the data analysis toolpack. Now, as an example, let's go back to the model that we've used a couple of times now. In this particular case, you've seen this data already. Have a data set. I've shared it with you with 500 households and a number of different variables associated with things that might relate to the household's monthly housing payment. Amongst those is total debt, family size, location. Now, we've discussed on the surface, we've discussed the notion that location is a qualitative variable, and I've asked you to accept that in order to include that qualitative variable in our model, we have to incorporate 3 of the dummy or indicator variables associated with those 4 levels of location. Remember, the location was coded 1, 2, 3, and 4 for the 4 regions of the neighborhood. Now we're going to discuss qualitative variables and the use of indicator variables in much more detail later, but for now I'm hoping that you accept that we have to, if we want to include location, we have to include 3 of the 4 indicator variables associated with location. If we included 4, we'd have a computational problem in finding x transpose x inverse. I've already mentioned that briefly, but we will investigate that in great detail in another presentation later. And we also talk about the income of the first wage earner, the average monthly expenditure on utilities, and the residence being owned or rented, another qualitative variable as being the predictive variables for what I've called the full model. And we've run this full model, and we've gotten the output associated with it. By now, this output should be familiar to you. If it's not, then you ought to quickly go back and review the various Excel workbooks that I've made available to you. Now, associated with this particular presentation is another workbook called the Payment Testing Solution Excel workbook, and of course you can access it via the lesson in our classroom. You've seen this stuff before. We've run this model, and now I want to delve into it a little more deeply. You'll notice that here is the value of here's the estimate for the regression parameter associated with these 8 variables in our model. Let's look at family size. B1, if you will, is minus 40.79. And the standard error associated with B1 is 12.3. So if we take B1 minus 0 and divide it by 12, we get minus 3.3. So that's the test statistic value associated with testing whether or not the regression coefficient associated with family size is equal to 0. And notice, we could do that test, we could find the critical value, but we don't need to, because Excel actually gives us the p-value associated with that test statistic. And that p-value is 0.001. Now keep in mind, what's the null hypothesis? The null hypothesis is that the regression parameter associated with the variable family size is equal to 0 versus not equal to 0. And you might remember, I've said it before, the ditty that you'll want to keep in mind is if p is small, reject the null. And in this case, the p-value associated with testing the significance of the regression parameter associated with the variable family size is quite small, 0.001. And so we reject the null hypothesis in favor of the alternative being that the regression coefficient associated with family size is not equal to 0, which means then that family size, in the presence of these other 7 variables, significantly improves the explanatory power of the model. And so we would want to keep that particular variable in our model that we're using to study the relationship between monthly payments and other explanatory variables that you see listed here. Now, contrast that with the p-value associated with the test of the ownership regression coefficient. In this particular case, the test value found by taking 74.72 and dividing it by the standard error associated with the ownership regression coefficient gives us a value of 0.719. And more importantly, take a look at the p-value associated with that test. The p-value is 0.47. Now remember, reject the null if p is small. Well, 0.47 is certainly not small if it represents the probability of making a type 1 error. And so we can see that in the presence of the other 7 variables, family size and these others, that ownership certainly does not significantly contribute to the explanatory power of the model. And of course, take a look at the confidence interval associated with that regression coefficient, and it includes 0. Similarly, the p-values associated with testing whether the regression coefficient associated with first income and utilities are both humongous. They're very large. And so in this particular case, for each of those 3 variables that you see with these large p-values, we would be unable to reject the null hypothesis. That is, we would conclude that in the presence of the other 7 variables, ownership does not significantly improve the model. First income does not significantly improve the model. Utilities in the presence of the other 7 variables, the utility payment, does not significantly improve the model. Well, I'm going to take that just a step further. And I've discussed this tangentially previously, but what I want to do today is I want to give you the underpinnings of how we can test whether individual predictor variables or blocks of predictor variables, that is, we want to test whether they, individual or blocks of predictor variables, significantly improve the explanatory power of the model. And the tool that enables us to do that is an f-test. We call it a partial f-test. Now, before we get too much further along, let's just go back and remember what we're trying to do when we fit a regression model. Whether it's a simple linear regression model or a multiple linear regression model, we are trying to reduce the sums of squares error. Well, if adding additional variables significantly reduces the sums of squares error, that would be a good thing. And we would want to include that variable or block of variables in our model. On the other hand, if including an individual or a block of predictor variables to a model that already contains some other predictor variables does not appreciably decrease the sums of squares error, then it's not worth having those additional variables in the model. Say that to yourself. Understand the logic behind the test, and then being able to conduct the test will be a much simpler thing to do. Now, of course, instead of looking at reducing the sums of squares error, we could look at just the opposite approach. We could look at whether or not adding an additional variable or a block of variables to a model significantly increases the sums of squares for regression. Now remember, sums of squares total equals sums of squares error plus sums of squares for regression. So if we decrease the sums of squares error, then we have to, by the same margin, increase the sums of squares for regression, because the sums of squares total is fixed. So we could, and our textbook does, instead of using a partial f-test associated with sums of squares error, use a partial f-test associated with sums of squares for regression. Or, equivalently, we could use a partial f-test associated with r squared. If adding additional variables to a model appreciably increases the value of r squared, that would be a good thing. If, on the other hand, adding an additional variable or group of variables to a model does not appreciably change the value of r squared, then what's the use? We would not then want to add those variables. So we have three approaches. I would ask you to take a good look at the homework solutions that I've generated. I've tried to make the connection for you that using r squared, using partial f-tests on r squared, on sums of squares for regression, or sums of squares error, all lead us to exactly the same place. So it's just a matter of personal preference. My preference is using sums of squares error, because from the very beginning I accepted the notion that when we build multiple linear regression models, our real goal is to try to minimize the sums of squares error. And if including additional variables into a model appreciably reduces the sums of squares error, then in my way of thinking, that's a very good thing. And so we can conduct a partial f-test. It turns out, because of the normality assumption, that when we take the sums of squares error for the reduced model and subtract the sums of squares error for the full model and divide that by the appropriate degrees of freedom, and then divide that result by the mean squared error associated with the full model, we have a test statistic that has an F distribution with degrees of freedom associated with the difference between the sums of squares error degrees of freedom for the reduced and the full model, and in the denominator the degrees of freedom associated with the sums of squares error of the full model. Now clearly, if f is big, we'd be inclined to include additional variables, because if f is big, then that means the sums of squares error for the full model was much smaller than the sums of squares error associated with the reduced model, which means then that adding additional variables to a smaller model significantly decreased the sums of squares error, which is what we would want to have happen. So large values of f star lead us to the conclusion that the regression coefficients associated with these additional variables are not zero. That is, that including them significantly improves the explanatory power of the model. Now, unfortunately, Excel does not do this automatically for us, but we can certainly run the full and the reduced model, and we've already done that in a previous lesson. I'm going to go and review that again with you in the context of this partial f-test, and it's going to confirm what we logically concluded in our previous lesson. So let's go do that. Let's go to the Excel workbook, and again you'll notice that the reduced model includes family size, debt, LOC 1, LOC 2, and LOC 3. That is, we've eliminated these three variables: ownership, first income, and utilities. And our reduced model in this case produces, and you've seen this already, these estimated regression coefficients. The model is highly significant. We talked about this in a previous lesson. And what I want you to pay attention to at this point is that the sums of squares error associated with this reduced model is 295,19101. Now, adding the three additional variables of ownership, first income, and utilities only brought our sums of squares error to 293,55295. And if you go back to this worksheet, I've written them out for you here so that you can stare at them a little bit. The sums of squares for regression, sums of squares error for the reduced model was 295. We add those three additional variables, And the sums of squares error, of course, gets reduced. But the question is, does it get significantly reduced? That is the difference between 295, 19101 and 293, 55295, is that significant? Well, let's do the test. And it turns out that the test value associated with this statistic is 0.913. And the question becomes, is 0.913 big? And the answer to that question is, no, it is not. The p-value associated with this test is 0.4344. The critical value, if you wanted to do this test using a critical F value, is 2.62. And so 0.913 is not greater than 2.62. So at the 0.05 level, we would conclude that the additional variables do not significantly improve the model. But even if we ran the test at a level of significance of 0.43, we would still conclude. No one would want to do that, by the way. No one wants to take that risk of making a type 1 error, being wrong. But even if you were willing to accept such a hellacious p-value or level of significance of 0.43, you still would not conclude that these three additional variables significantly improve the model. And so, we're left to, in this particular example, to conclude that those three additional variables do not appreciably increase the explanatory power of our model. And so, from a logical standpoint, there's really no need then to include them. In fact, if we do include them, their interpretation becomes confounded. It's very confusing to interpret. Now, as I mentioned, we could do the partial F test using R squared, and the result is absolutely the same. It's mathematically the same. And if you did the partial F test using sums of squares for regression, the mathematics would be the same. And that is because there is a identity that links sums of squares error, sums of squares for regression to sums of squares total, and sums of squares for regression and sums of squares total then to R squared. And we've seen those formulas before. So we could do the same test, same partial F test using R squared. And of course, in this case, if we start with the reduced model, the R squared value is 0.529. And if we include those three additional variables, the R squared value jumps to 0.53. And so, the question becomes, is 0.53 associated with the full model a significant improvement over 0.529, which is the R squared associated with the reduced model? And the answer is clearly no. Now, we'll take a look at the test statistic in just a moment, but just plain old common sense seems to tell me, well, I guess I shouldn't say that, because sometimes things that appear to be common sense really aren't. And so we should probably just let the numbers speak for themselves, and so I will do that. But I can't help but say, parenthetically, 0.53 doesn't seem a heck of a lot bigger than 0.529 to me. But let's do the test. And lo and behold, when we take the difference between the R squares associated with the full model and the reduced model and put them into our partial F test, we get that value of 0.913, which is the test statistic value that we got using the sums of squares error approach. And again, we will test that against the critical value, or we can compute the p-value associated with the test in the same way that we did previously. The bottom line is that using this formal partial F test, we can certainly conclude that adding those three additional variables to a model already containing the 5 variables does not significantly improve the explanatory power of the model. And so our conclusion is that the regression coefficients associated with those 3 additional variables are in fact equal to 0. That is, they do not significantly improve the model and therefore can be eliminated from the model. Now, we can do t-tests for individual variables, which we've already discussed, or we can do a partial f-test by adding one variable at a time. The results are going to be the same. And if you're inclined to do that, I would ask you to go ahead. But I just want you now to feel comfortable with knowing how we can test whether adding variables to a model is useful or not. Useful in the sense of increasing the explanatory power of the model through the reduction of sums of squares error, or the increase of R squared, or equivalently sums of squares for regression, because that's our goal. And so I would ask you to take a look at the reading for this week's lesson, including standardized regression models and multicollinearity. Please don't forget to do that, and review the materials associated with this video presentation, and of course take a look at the homework. And then hopefully you'll master this material and be ready to move on. Thank you.